Morning, everyone. I will present the case study at the ELSA dairy industry. The outline is as follows. First, a big picture, then some words about energy efficiency at ELSA, then why SIP cleaning in place processes has been selected as a candidate process for HTHP integration, what is cleaning in place in a few words, why measurements and what are the measurements that have been taken, the result, and very short bench analysis to derive the heat pump integration concept, a comparison of different heat pump concept, and conclusion. So first, ELSA has been founded in 1955 as a canning factory, and it evolved quickly to dairy industry since 1960. The site has undergone a step-by-step expansion over the years, and in 2021, the key data about employees, 72 gigawatt hours heat, of which 20% gas and 80% wood chips, 42 gigawatt hour electricity, and a huge amount of city water. And as regards the production, 260,000 tons milk per year is processed into various products. It also produced a plant-based product, but is still negligible compared to dairy products. So energy efficiency has a long history at ELSA. There are various local opportunities that have been implemented. Measure in the last decade were focused, for example, on ice water production, efficiency, distribution, waste heat recovery loop from different processes. And in 2013, a pinch analysis has been conducted. There were different measures proposed inside the process optimization, as well as a site-wide loop with a heat pump integration. Some of them have been implemented, but the site-wide heat pump has not been, because in these industries, and in particular at ELSA, it is so packed in the premises by piping and so on, so that almost not possible or very difficult to retrofit and to install the pipes, and so it is a major constraint. And in 2016, I think, a wood chips steam boiler has been installed, and after some optimization step, the production, steam production by this steam boiler reached almost 80%. One of the measures was the merging of two separate networks. One was for black steam, and the other one was for steam used into the production, for example, vaporization process. As I said, there are hard constraints, and there is very, very little free space for installing heat pump, piping, storage. The cleaning in place process, here you see the station number 0. In fact, works with water, steam, and release wastewater with an average temperature of about 35 degrees. The interesting things about CAP station is that they are at the same place. They represent a large fraction of the city water consumption. There is no measure of the steam consumption of the steam CIP station, but yeah, ELSA estimates about 15 or even more steam consumption. The other advantage of considering CIP is that there are two sources, waste heat sources nearby. One is, of course, the wastewater, and the other one is the ammonia condensation heat from the chilled water production, which is just very close to the SIP station. And it leaves the production process unchanged, so it's also advantageous. And ELSA proposed had in mind two integration concepts. One was at the supply level, so producing steam to substitute steam from the steam boiler, or an ammonia heat pump to heat the water that is used as makeup water for the SIP station. A SIP station looks like this. It has different, the SIP station has different tanks. So this is soda tank, acid tank, a recycled water tank, and a fresh city water tank. And here are the different circuits. Each circuit cleans different equipment. And these are the return lines, the flow lines. And it includes 5 steps. I don't want to go into details. The first step is pre-rinse with the recycled water. First with clean water to remove the product from the pipe, and then recycled water, followed by a circulation of caustic solution, and an intermediate rinse with recycled water, then circulation of acid solution, and finally a final rinse with fresh water. So that's the typical procedure for cleaning in place. Of course, these stations have control system from which we can get information, but no information about heat consumption, where and how. If we analyze the system, there are 3 places where heat is used. First, steam heating, temperature holding of the tanks, and also indirectly heating the makeup water that comes into the tanks not by a heat exchanger, but direct steam injection. So this is for the soda tank and also for the acid tank. And to adjust the temperature of the flow to the specific temperature required by the different equipment to be clean, there are also, I forgot to mention that recycled water is not heated, and to adjust the temperature for each circuit, we have inline heat exchanger. Here it's not steam injection, but steam heated heat exchanger. And for the SIP0, there are 11 circuits. In total, for the 3 SIP stations, there are 37. We cannot measure every circuits. We took 2 circuits, circuit B and C, to analyze how heat is supplied to the different circuits, and when, at which step of the cleaning procedure. So the goal was how much heat is supplied where, from the tank, in the tanks, or through the inline heat exchanger. What are actually the required temperature? So yeah, we undertook measurements, and the result, as regards the inline heat exchanger, first we see on the left and in dotted blue line, it's the temperature before of the solution before the inline heat exchanger, and in red, the temperature after the heat, the steam heated heat exchanger. And see here we see a sequence of three sequence of cleaning in place. We see exactly the same on the circuit C, with the same convention. So blue before, red after. It's the time scale here is 3 hours, and what we see is that the recycled water is heated at different periods. First, here we have the pre-rinse. Here we have the soda. Here the intermediate rinse. Here the acid circulation, and then the final rinse. And the final rinse first is the fresh water is first heated and then not heated. And the sequence, yeah, we see that for the recycled water, we have almost the same situation in circuit B and C. So preheated, heated in the pre-rinse and during the intermediate rinse. We also have, particularly in the case of circuit C, heating of the solution, the soda solution, the caustic solution. Also, in both cases, for the acid solution, the solution is heated by the heat exchanger, and as regards the final rinse, the city water fresh city water is also heated during the first part of the cleaning, the final rinse. So the idea was, okay, but it seems that if we look at this graph, it seems that the temperature set point of the acid tank is too low, and it is systematically heated by the heat exchanger, inline heat exchanger. And we also see that the recycled water tank, which is not heated, in fact, is, yeah, on average, too low, so that it is also heated by the heat exchanger. The problem is at ELSA is that we cannot, the constraint was we cannot retrofit the 37 heat exchanger, steam heated heat exchanger. There is no place for that, and it would be too costly. So one of the solution was to shift, we envisage, was to shift a big part of the presently heat supplied by the inline heat exchanger to the tank by changing, optimizing increasing their set point temperature. Of course, we cannot do the whole 100% because probably we have different set points in the circuits. But yeah, we can at least shift a big part of the heating, which is presently achieved by the inline heat exchanger, to the tanks. That was the idea. And regarding the heat and water balance, we also, as I said, measure what happened at the around the caustic and acid tanks to see how much heat was supplied to hold the temperature and how much makeup water was supplied. And we got this diagram. Here in red, we have the temperature holding of the caustic tank, which is responsible for over 40% of the heat, of the steam consumed. And also we have here, in particular in green, the the heat that is supplied by the heat exchanger, the inline heat exchanger during the acid wash. And this in blue is the heat consumption, or the heat supplied by the inline heat exchanger during the first phase of the final rinse. So yeah, we could also calculate and extrapolate for the 3 station how much makeup water it represents over the year. One thing which is surprising is that the acid tank, in fact, requires very little temperature holding, heat for temperature holding, because the return of the return lines have a higher temperature than the flow temperature. So it is heated externally by other by the circuits which are, or the equipment which are cleaned. Yeah, because here in the acid, in the soda caustic tank, the temperature holding is very large, while for the acid tank it is quite low, or very, very small. We mentioned the pinch analysis as a tool to check the integration of, optimize integration of heat pump. And I just want to show that if we consider at first the process as a black box, we see that we need steam at 4.5 bar absolute, and makeup water which comes in cool. Oh, yeah. And so what we see as a temperature, as a heat requirement versus temperature, we see that we have finally water that must be heated and evaporated to produce the steam that the CIP station will consume. Now, if we look closer to the process, we see that we get this profile, so the heat versus how much heat versus temperature. Here in this case, still the makeup water is not heated, preheated. And if we go to the real actual requirements of the system, we have again a decrease for part of the heat requirement. We have a decrease of the temperature level. So each time we can decrease the temperature of the requirement, this means a higher higher potential for efficient heat pump, so higher COP. What we get after from these measurements, we can draw the composite curve. Here we have we consider only the condensation of ammonia chillers as a heat source, and as a heat sink we have the heating of the makeup water, and we also have the recycled tank heating, so that the temperature, we increase the temperature of the tank so that we reduce the inline heat exchange, the heat supplied by the inline heat exchanger. And the same for the acid tank, which is quite small, as I mentioned, and for the soda tank, we have a quite large heat demand. So this is the basis or the start for integrating the heat pump. I don't want to go into details here. I have listed what is not included for different reasons in this composite curve. But I would stress that these are average composite curves. So it considers that the heating or the heat requirements of the CIP is constant over the year, which is in fact not the case. And also, this important to mention is that this composite curve consider that we have a conservative estimation of the possible shift of the heat and possible how to say, fraction of the heat supplied by the heat pump, because as we will see this on this graph, I think we see this, the SIP activity, unlike processes, continuous processes, for example, is very variable. Here we have in blue the total consumption of water over 1 quarter of hour over 1 week. And we see that, of course, in the morning there is little activity. It increases over during the day, and the cleaning activity reaches a maximum around midnight. And of course, during the weekend it is less, but there is still activities in the dairy. So the problem is a sizing problem for the heat pump. What size of the heat pump, of storage, to ensure that we have a reasonable trade-off between the capacity and the capacity installed and the savings. It's not reasonable to have a capacity which is of the heat pump and storage, which allows to cover the whole the maximum or the peak, the average peak during a short period. Here we see a classified curve of this cooling water, which is a consumption, which is a good indicator of the level of CIP activity. And we see that even if we can store for 1.5 hours with a heat storage, we still have peaks of 150 cubic meter per hour, while the average is about 60. The mean is about 60 cubic meter per hour. So there is a sizing problem. I don't want to go into details. So the solution or the integration concept that we can derive from this composite curve, in fact, combines two different technologies or different cycles. One is a transcritical cycle, transcritical CO2 heat pump for preparing, for heating the makeup water with a high COP. And this is confirmed technology of the, it will be a off-the-shelf machine. And one solution to provide the heat to the tanks, to the recycled water tank and the acid tank, could be ammonia with 2 circuits, 2 temperature heat pump, of course, also with 2 storage for the reason I showed just before. One would have a rather high COP for heating the recycled water, and the second one a lower, of course, COP, but also a lower contribution. So maybe it's not so so useful. Yeah. But in overall, we have a COP of 4.3, which is good, but quite complex. And the reason why we leave this away, or we don't have a heat pump, is that because the temperature is quite large and the COP would be low. And if we install the first 2 heat pump, which has a higher COP, we won't have place enough free space for the required heat storage for this additional heat pump. Here is the schematic diagram, how it would look. Here we have the CO2 transcritical heat pump for preparing the hot water to supply the tanks. And here the two circuits for the two different tanks for heating and temperature holding. If we compare the concept now, yeah, there are maybe more concepts to consider, but this is the first idea, that integration at the supply level. It would have a large savings. The integration would be quite simple with little change, but yeah, there will be no or almost no storage capacity on the steam side, and the profitability would be very low, if any. If now I compare to the solution I just described with this combined transcritical CO2 heat pump and ammonia heat pump with two temperature, we have high overall COP with a good savings. These are the benefits are standard technology, high overall COP, so low OPEX, and yeah, good. Yeah. From this point of view, it's good, but we can ask whether the heat pump for the AC tank makes sense due to the small contribution and the additional complexity it adds, a heat pump and storage. Maybe it's not worth. And of course, the capex and the integration would be rather difficult. It is important to mention that the savings in terms of CO2 is not high because of the mix, the steam production mix made from 80% of wood. So in this case, if the goal is CO2 emission reduction, it's not so beneficial, the heat pump. It has other advantages, but from this point of view, not good. And the other thing is, in the COP calculation, I did not include the reduction of the electricity consumption of cooling towers. We have no data regarding their operation, the operation strategy to calculate the savings. Now the conclusion, the CIP process is energy intensive and tricky because of this stochastic operation, and so it leads to difficulties in the sizing. Again, we see that process knowledge is key for energy efficiency. In fact, high temperature heat pump is not needed. Standard one or standard ones are okay. We have different reasonably interesting concept with different profile, different pro and contra, which are to be compared. Yeah, as I said, this solution or this integration concept is one maybe should be reviewed or simplified. In this case, due to several change in the mind of ELSA, we were not able to get OPEX estimates, or at first also reasonable simulation to to calculate this trade-off between heat pump and storage, for example. And of course, the capex has not been calculated. And also, heat pump and wood chips in some way are competing in the CO2 emission reduction. And from this, we could say, okay, begin with heat recovery and heat upgrading before resource substitution, and not vice versa. Thank you for your attention.
Thank you very much, Pierre.